Hi everyone, welcome to this lesson on applications of similar triangles. So let's say, for example, you're at a resort or something with your parents maybe, and you're in a nice tropical destination, and you're walking along the beach, and you happen to see a really big tree, like a palm tree, and you might wonder how tall is that tree anyway? I mean, one way you could figure that out is you could climb it, I suppose, with with a rope or a tape measure, and then either measure the rope or just look at the tape measure or whatever. But that's a lot of work, and you might fall out of the tree, and then you won't look cool, and your friends will laugh at you, and whatever. So that might be embarrassing. So here's another way that might still be embarrassing, but at least you'll be able to figure out how tall the tree is without having to climb it. Okay, so to set this up, let me just remind you a little bit about similar triangles and how we might use them. So here's a typical case where you say, okay, find the height of a flagpole whose shadow is 14.5 meters long, and at the same time of day, a 1.8 meter tall person casts a shadow 2.5 meters long. So here's here's the flagpole rather. Here's you. Here's the shadow of the flagpole, and here's your shadow. Okay? So basically, what do you know? Well, if we write in if we write in the information that we have, right on the diagram, the flagpole, it says the shadow is 14.5 meters, and the shadow of the person is 2.5 meters, and the person is 1.8 meters tall. Okay, and although it's not really said, the sun is over here somewhere. Okay, so there you go. So that's basically what we have. Now, what are we trying to find? The height of the flagpole. Okay, we're trying to find the height of the flagpole. That's what it says there. So we're going to call that x. Let x be the height of the flagpole. Height of flagpole. Okay, you get it. Okay, so similar triangles, right? Maybe? Perhaps. How can I convince you that these are similar triangles? Well, it might be a little bit of a stretch, but essentially you can see that they are both right angle triangles, right, by construction. And what you have to imagine here is that the angle that the shadow makes with this ray of sunlight, so here's this ray of sunlight coming down, the angle that that ray of sunlight makes with the ground is the same as this ray makes with the ground over here. Right? So that's basically what we're assuming, that we have an angle similarity. So we can use our similar triangles. Specifically, we can use the idea of a scale factor. So if you look at the triangles here, you see that we have the length of the shadow. Those are the two sides that are related, so we'll use that as our scale factor. So we're going to take the long side and divide it by the shorter side, and we get 5.8. Okay, 5.8. So that's going to be our scale factor. All right. So then, looking at the diagram here, we have the height of the person, which we know, 1.8, and the height of the flagpole we don't know, but we know that if we are going this way, we multiply by our scale factor. So our flagpole height, x, is going to equal 1.8, the person's height, multiplied by the scale factor, 5.8, which is going to give us 10.44 meters. Okay, so that's the height of the flagpole, 10.44 meters. Let's just do a nice little paraphrase here to actually answer the question. Therefore, the height of the flagpole is about 10 meters. Okay? we get the idea, right? If I see that this work, if on a test, some of you might wonder, well, we rounded here, but that's okay. If I see the work that you've done here, you've done all this, you've set your diagram up, you've explicitly stated what your unknown is, and so on and so forth. If you just say it's about 10 meters, hey, that's cool. For our purposes, that's certainly close enough to reality. Okay, here's a slightly different setup, and if you're wondering how this works, I'm going to link another video in the description of this video so you can watch how to do this in real life, in actuality, because it's pretty cool. But basically what you do is, another way to do this, like let's say for example it's not a particularly sunny day, so there isn't a shadow to use. You might still wonder how tall a tree is, and given where we are in Canada at this time of year, we can't really rely on there being a sunny day. So this might be something that we have to resort to. So basically what you do is you set up a mirror partway between yourself and the object that you want to measure, a tree in this case. So what you do is you stand back from the mirror until you see the top of the tree in the mirror, right? So you're looking in the mirror at all times. Yeah, so this is actually pretty cool, and it's a little hard to describe with just a picture like this, but if you watch the video that I link, then you'll see a little better how this works. Anyhow, if we just, on our diagram, put in some numbers here, we see that the Steve is 1.6 meters tall, so we'll just put that in, 1.6 meters. The mirror is 2.5 meters from the tree, and Steve is 1.75 meters from the mirror. 7.5, okay? So there you go. Those are our distances. And once again, we know we have a similar triangle situation, or well, we infer we have a similar triangle situation because we have a right angle here, a right angle here, and this angle should be equal to this angle. Now that might not be obvious from the diagram, but it's a consequence of physics actually, that angle in has to equal angle out. If you're taking science this semester, you might ask your grade 10 science teacher to better explain that to you, but for now, for the purpose of this video, that's what's happening. So we have an angle similarity. Okay, so in this case we set up our scale factor. Excuse me, first of all we're going to shrink this a little bit, and we're going to say let x be the height of the tree. You get the idea. I feel like I need a pen when I'm doing this sometimes. My finger isn't that precise. Okay, so then we're going to set up our scale factor. Again, we're going to divide the larger one by the shorter one in the hopes that we get a nice number, or at least a number greater than 1. In this case, however, if I actually check in my calculator, if I divide 2.5 by 1.75, I get a pretty nasty decimal. It's a non-repeating, at least as far as I can tell, decimal that goes on forever. So I'm just going to, you know what? For now, I'm just going to leave the scale factor in this ratio form, in this fractional form. So I'm not actually going to. Oops. So I'm not actually going to work it out past this point. Alright, so that's my scale factor. It's just a ratio, whatever, no biggie. So then, just like we had before, if I take Steve's height, and I want to use it to get the tree's height, since the tree is taller, I have to multiply Steve's height by the scale factor. So in this case, x equals 1.6 multiplied by the scale factor, so 2.5 divided by 1.75. Okay, so now of course you would pull out your calculator, and you would get approximately, again it's not an exact number, but you would get approximately 2.29 meters, okay, for x. Yeah, so that's basically that. Again, let's write up a nice conclusion here. Okay. Therefore, the tree is about 2.3 meters tall. Okay, so that's a very typical question. Again, please do check out the link in the description below, the doobly-doo as it's known, and yeah, you can see how this works in real life. All right, thanks.